So till the last lecture, what we were discussing was about the concentric loading. And what we discussed is that if the load P is coming from the columns onto the isolated footing, and we say that the stresses or that develop due to the soil pressure onto the rigid foundation or the rigid footing, which we are actually assuming it to be rigid, is Q, and that Q has to be less than QA, where QA is the allowable soil pressure. And this actually depends upon the bearing capacity of the soil. And we usually take QA to be the bearing capacity with the factor of safety being 2 to 6 here while determining QA from the bearing capacity. So we assume that the distribution of the soil pressure is uniform for in case of concentric loading, where A is the area of the footing. So thereby Q would be P by A. Now, in the case of eccentric loading, you have a load P that's acting through the column. Now, if we also take into account the self weight of the footing, which is delta P, then the total load would be P plus delta P. Now, delta P is usually taken as 10 to 15% of the value of P. This is just in a thumb rule that we are using in order to determine the self weight of the footing. So thereby, the total load will be P plus delta P. So the reaction that would be offered by the soil to this load, P plus delta P, would be R. Now that reaction, because now the load is at an eccentricity E from the center. This red line is from the black line is at E distance. So thereby, a moment M is generated in the column, and that M is P into E. Now, once we know the moment M being P into E, thereby now how would the soil pressure would actually act? And in the concentric loading, it was uniform, P by A stress, the soil pressure. But now here two cases would arise. Case one, where the eccentricity is less than L by 6, meaning you have the low eccentricity at 1/3 of the from the center. So now, why do we take it at L by 6? That we'll come to know during this discussion. E is M by P plus delta P, because M is P plus delta P into E, P plus delta P being the total load. So once we know the total value of E now, and we know its location, it being less than or equal to, it could also be equal to L by 6, thereby and we can say that in this case, what we'll come to know is that there is a total contact area between the soil pressure and between the soil as and the footing. Now, how does that happen? We'll just be seeing that there is no, but this soil pressure, you have to remember now, is not uniform like it was in the case of the concentric loading. It's a non-uniform load that would be varying from certain Q minimum to Q maximum. Now, corresponding to these two, there would be a point where it would be Q maximum, and there would be a point where it would be Q minimum. So let's have a look at this. This is Q minimum here, and there is a point at which it's Q maximum. There's a point where it's Q minimum, and there's a point where the pressure is Q maximum. Now, it's natural that the Q minimum will be on the opposite side, where from the load is not acting. Because the load is acting more towards this right side, so the stresses will be more towards this side. So now we can say for E being less than or equal to L by 6, the Q minimum, the total foundation is in contact with the soil. There is no uplifting of the foundation from the soil, meaning there is no stresses developing which are actually going the tensile way within the soil, or the pull out way. So how do we calculate them? First of all, the Q maximum. Uh, let's determine the value of Q maximum here. How would we determine the value of Q maximum? That would be based on P plus delta P. It's delta P divided by A. Now, what is this? This is the maximum stress that could act in the now this is the maximum stress that could be acting due to the load itself. Now, plus to that, you have, so this is P by A is the maximum stress due to the load, and then you have the stress due to the movements. And what is movement induced stress? That's M by Z. So, or M by Z. So, once we know M by Z, now how much is M by Z? M is P plus delta P, and that's multiplied by E divided by, so that's M by Z. This is Z. Now, what is Z? The value of Z. Uh, Z is the equal to BL square by 6. How do we know that? Uh, it's BL square by 6. Yes, how do we know that? We know that because we know the value of I. What is I? Uh, the value of I is BL cube by 12. So you have Z equal to I by L by 2. Thereby, you have this Z equal to BL square by 6. So Q max is then finally equal to what? It's if Z is replaced by BL square by 6, and we then would have the value of Q max equal to P plus delta P divided by A. This is multiplied by P plus delta P and divided by A. 1 plus, this would be 6, because Z will be BL square by, so BL will be equal to A. So what will remain will be just L, and 6 will go towards the top. So you will have 6E by, so this is plus minus actually, plus and minus 6E by L. So this is the, now this is minus here, plus minus, and this is plus minus. So it could be plus or it could be minus. Now this is then you are actually getting the value of, so uh, when we are introducing the value of minus here, then it also we are also getting the value of maximum with minimum. So uh, then we are also getting the minimum value, and here also. You are getting the value, minimum value here. So thereby, uh, Q maximum would be 1 plus 6 EAL, 6 E by L into P plus delta P by A, and Q minimum would be 1 minus 6 E by L. Now, um, now here, this is important. Our condition that's E was less than or equal to L by 6. Now, for example, E is equal to L by 6, first of all. In that case, uh, can we just recall what would happen here? This would be L and by 6, so this would be 1. So the maximum value of Q would then be, mm, that would be P plus delta P twice. Now this is twice P plus delta P by A, and the minimum value is Q minimum would be 0 here. Now very important to know that this is then becoming, a value is becoming 0. So in that case, once you have E equal to L by 6, the uh, number one, the maximum contact is 2 P plus delta P by A, and the minimum is 0. This is 0, and this is 2 P plus delta P by A. So this being the Q maximum. So you are getting a triangular load. This is a non-uniform load distribution or the soil contact pressure, and thereby the stresses that are transmitted to the soil and the soil reaction that's offered is not uniform, but all of the soil is in contact with the uh, with the footing up till the case of E less than or equal to L by 6. Uh, and none of the part of the soil is actually, the soil is offering the reaction to the footing in such a way that the footing is behaving in the way that we already have seen in the concentric loading. How it's, we just checked this when we were doing the concentric loading. This, so if we rotate this by 180-degree, so this becomes cantilever. So there is hogging at the ends of this. So when you have hogging at the ends, that means there is a tension. There is tension at the towards the ends, towards the top, but it's actually towards the bottom. So towards the ends, the footing is actually behaving with tension at the bottom, and at the center there is tension at the towards the top. Now that's the case when there is a soil pressure exerted from below. But if now, that's case number 2, what happens in case number 2 if E is greater than L by 6? This is case number 2. What would happen in such a case is that, first of all, there not the all of the footing is in contact with the soil. That's the first thing. Uh, this is Q minimum, and this is Q maximum. So not whole of the soil is in contact, footing is in contact with the soil. So now what is Q minimum here? It's corresponding to, it's 0 for at a particular location. Now, how do you define that? That's very important, uh, because here once if I when E is greater than L by 6, the equation that we had here, this one, this is becoming invalid because this comes out to be minus the value of Q minimum, and that means uh, a value of Q minimum being negative means implying a tensile force at the interface. Uh, but practically, soil has no tensile capacity. As you are aware that concrete itself has little tensile capacity, soil has almost zero tensile capacity. Thereby, uh, once we are assuming a triangular distribution of the so thereby the tensile capacity, because the soil is minimum zero, almost zero tensile capacity, thereby there is no point if we say that this portion is coming into tension, then there is no point in saying that because uh, the soil has zero tensile capacity. Thereby, once that's the case, when the soil has no tensile capacity, we can say practically that's impossible. So, and what would happen in that case? Uh, and we have a maximum value only on one side, at one direction. So thereby the problem is essentially here, it's a uniaxial eccentricity problem. Uh, and being a uniaxially eccentric problem, uh, and having a triangular distribution of load, soil being under compression on the right hand side here, in this figure, being here on this side being in compression. So we have a we can say there is a collinear line of action of the resultant soil pressure with the concentric load, and that's R, and because R is equal to P, because R, the value of R is P plus delta P. So we can say there is a line through which this resultant is distributed within the setup here. Uh, there would be a point at which the resultant R, P plus delta P, is actually acting within that right hand side. So thereby, it's very important that we have a collinear line of action of the resultant soil reaction, that's R, with the eccentric load, that's P plus delta P, which is acting from the top. So you have, uh, now why is this important? This is important because of the system has to remain stable. Now, when does the system remain stable? Uh, what is the natural tendency? Left side जो है, its tendency would be, because soil has got zero tensile capacity, the tendency would have been to uplift it, but it cannot even uplift itself on that side, because soil is offering no reaction from the top. So there is almost zero contact between footing and the soil on that side. So the resultant distribution of all the compressive loads is on the right side, which is the red portion here. And within that, you have R now equal to P plus delta P. Because now the contact area is less, so soil पे ज़्यादा pressure आएगा. And that pressure, soil pressure, has to be taken up by the part of a soil which is in contact with the part of the footing. So it would depend naturally on the amount of eccentricity. So greater the moments now, lesser is the contact between the soil and the footing. So less effective is the footing uh, actually becoming. So first of all, we need to avoid great large eccentricities within the system, within the structure. And then while we are designing the footing, you have to take into account that all your footing should be at least equal in contact with the soil uh, while you're designing it. But now, if that is crossing, like E is greater than L by 6, then we have to redesign the system for a case where uh, the resultant soil pressure is still manageable within the limits. Uh, so thereby, at this point, we are now aware about the soil pressures which are coming onto the onto the footing from which the footing design is on which the footing design is actually based on. So till now we have focused on two things. One is the what is the distribution of the pressure onto the footing from through the soil, and how does it vary between the concentric and the eccentric loads. That was the first thing. And what was the allowable soil pressure, uh, what relation does it have with the bearing capacity of the soil. So these were the two things on which we were focused as of now. Now in the next we would now be talking about what is the can we actually eliminate eccentricity in the loading? Yes, we can do that. How do we eliminate eccentricity? We and it actually depends upon the degrees of certainty and or the degrees of freedom uh, of the load. If we make the joints rigid, and we're trying to arrive at its design which is actually economical, and then we also if we can also eliminate the eccentricity by making the sections uh, symmetrical. We can eliminate the eccentricity by making the sections such that the load is equally distributed within the sections. So our focus should be to eliminate eccentricity. We cannot eliminate eccentricity as a whole, but large amount of eccentricities would lead to greater moments, and greater moments actually then what they do is that they lead to the soil failures. So our focus should be that we avoid the soil failures by uh, distributing all the load from the footing onto the soil. So for that, we need to establish a proper contact between the soil and the footing. And our area of the footing has to be uh, such that we are saving the material of the footing, and while we are designing the isolated footing or in a shallow foundation. So this was about the two things that we discussed until now. That was about the soil pressure distribution, and the other thing about the allowable soil pressure. So next we will be discussing about the overturning and the sliding effects that could happen in the footing. Now we all know that the earthquake loads or the lateral wind loads, they could act on the structure. Now all those loads lead to instability within the structure. You have a column and then you have a footing. Now if this is acted upon by an earthquake load, what is the natural tendency of this? The natural tendency within the soil structure is that if this is a soil medium, and this is the soil medium, what is the natural tendency is that this could just slide through the uh, soil, and we usually call that as sliding. Now this could happen uh, once you are not actually providing the enough uh, balancing act on the two sides of the column. For example, to prevent this, what we call as sliding, we could provide a shear key here. And the shear key actually increases the amount of friction within the soil. So that shear key is a good thing to be provided such that we prevent the sliding. To prevent the overturning of this system, of this isolated footing, what we usually do is that we keep a balance between this side and this side, the right side and the left side. Keeping a balance is a good thing because there is a one side becomes what we call as in the retaining wall for footings, we have a heel and we have a toe, just like in the foot. So, and if the heel and the toe are not balanced out, the system could actually topple over the about this footing. So there could be a toppling action about this footing. Now that toppling action that could happen would naturally happen if there is, for example, there is nothing here. Just for a simplicity's sake, uh, I'm just cutting this out, this portion. There is nothing out there, so it could just topple over. Why? Because there is no balancing stability force on the other side. So, so with in footings, we have to actually uh, take this into consideration, that we avoid the sliding as well as the overturning of the footing. Now, when you are talking about the design of the footings, what are the design guidelines for footing? Right now, we are talking about the isolated footing design. So, what are the design guidelines? Let's go through them one by one. Now, what comes to your mind when you are designing a footing? What is the first step that you would naturally go through? There are various guidelines. Let's go through the design steps and explain within them the guidelines for the design of the isolated footing. So, what comes to your mind when you are designing a footing? What should be the first thing that you should be knowing? First of all, you should be knowing the bearing capacity, isn't it? We should be knowing the bearing capacity of the soil, and we should also be knowing the amount of settlement of the soil. These are very important to be known for the design of the footing. Uh, if now we know these things, the bearing capacity and the settlement of the soil, we can proceed with the design, because then we would be now knowing QA that we just discussed, the allowable soil pressure. Having known that, what else do you think is important? That is the load. Yes. Uh, we need, what is the amount of load on the footing? What is the amount of load on the footing? Now uh, is it truly an axial load, a concentric axial load, or is it eccentric axial load that's acting on the footing? So how much is the amount of eccentricity generated? How much are the moments generated within the, so that has to be known while we are designing the footing. Now, coming to the footing design, now we know we have already designed the roof, we have designed the beams, we have designed the slab, we have designed the columns, and we know the amount of infill now of the bricks that will go between the column frame, beam frame. So we actually now know the amount of load that would be coming onto the footing. So footing design would now be based on the total load that's coming from the roof up till the footing itself. And all that load has to be transferred into the soil. So we should be knowing that load as the axial load plus the amount of moments that are acting at particular point. So our step number one is actually very simple, is to determine the area of the footing, right? So our area of the footing is very important to be known. How would you know the area of the footing? In step number one, so you know P, you are aware of QA, right? So your Q should be less than QA, you are aware about that. So then, yes, if Q is taken as QA, you're getting the maximum amount of area. It's the minimum amount of area that you then require. So minimum area that you require is actually then Q, it's on that side, so it will be q by, let, let me say qa. This is qa, or q it will be equal to qa is equal to p plus delta p. I'm taking p as the total, p plus delta p divided by a minimum. So a minimum is then p by q, or qa. So your a minimum is p by qa, and we know this, and that the minimum area of the isolated footing is now p by qa. So clear? At this point, we actually know the minimum area of the footing that we require in terms of the allowable soil pressure. And so what should be our actual area now? Should it be greater than this? What does it depend upon? It depends upon the actual stresses that we have, and how much are they. Uh, yes, and you also need to take into account that you have the now the stresses that you that are acting, are they based upon the factored load? And what is the factored load? The factored load is here is service load. It's one into the total load that you have, because you are already taking, as I already discussed this, that QA, you have a factor of safety of 2 to 6, which is quite large while determining that. So we can easily go with the serviceability limit state criteria in this design. And um, yes, now what is the total what is the total contact area between your soil and the footing? That's very important. And plus, if we are avoiding that, what is the net soil pressure that is being exerted on the footing? That's very important. So these things are very important to be taken into account while we are designing. So having known the area of the footing, then you go to the step number 2, wherein you are actually now determining the thickness of the footing. So we now know the area, so we know the length and the breadth. Then we fix the uh, dimensions of the thickness. But let me share with you something. How do you define area? That's P by B into L. So what should be the ratio between L and B? That's quite important. What should be the ratio between L and B? Uh, is it 2 is to 1? Do you take 3 is to 1? It's very important to have a consistent length of the footing, uh, and such that you have a proper uh, design. Now, how do you take a consistent length of the footing? What's it based upon? It's actually based upon the ratio of the columns. For example, if you are having a column 300 cross 300 mm column, there that the ratio of the column length into breadth is 1, 300 by 300. So you would naturally be aligned to go for a footing of the length to breadth ratio of 1. Now, if you have a column of say 500 is to 300 or 600 is to 300, so you have the ratio of L by B of the column being 2. So again, then aligned with that, you could go for a footing with the alignment of length to breadth ratio of 2 is to 1. So you actually take the area of the footing in these terms. Very important to know this. Now, what is thickness based on? What was area based on? The area of the footing was based on actually the flexural capacity of the footing, um, wherein the footing is actually tending to undergo flexural stresses under the soil pressure. And we are designing the area of the footing in terms of that. What does the thickness of the footing actually define? The thickness of the footing is actually defining to us the how is it defined? It's defined by the shear capacity of the. So when we are talking about how to determine the thickness of the uh, footing, it's based on the shear capacity of the footing. Now there are two types of shears that usually act on the footing. First is the one-way shear, that's acting at a particular distance away from the column from which the load is being transferred, and on the both sides of the column, this the one-way shear would act uh, along the longer direction. The shear capacity needs to be checked more at a particular distance from the column. Now, this uh, is a shear which is actually due to the sharing of the two uh, balancing planes in which an unbalanced force is now being generated. So, because the load from this column would naturally be transferred along a particular plane like this. So, ultimately, most of the forces, there is a critical point at which the shear capacity is being checked within this plane. Now, this is a one-way shear problem. Then you would also have a two-way shear problem, which is also known as the punching shear. Now, what is a punching shear? Uh, there is a particular area about this right here. This uh, area about this on all four sides of the column in the footing, in which there is a punching action that would happen due to the load being transferred through the column. So it's actually a two-way shear problem. So this based on these two, that's the one-way shear, and on the two-way shear, the thickness or the depth of the footing can be determined. So this is step number two. Then we go to step number three, wherein now we are actually determining the once we have determined the thickness. Now we could go for the check of the base shear. Uh, so what about then the check for uh, what about the reinforcement? So the reinforcement is then provided, but it's based again on the flexural uh, capacity of the section reinforcement design. So how do we design for a reinforcement? Just to give you an idea that as we already discussed, there is uh, a compression at the top here, sorry, the tension at the top here, and that becomes tension at the bottom here. So likewise, you have the same situation on this face. So we usually need to provide, because below the column, we already have the reinforcement here of the rings from the column. So we usually need to provide the reinforcement at the bottom of the footing. So that is the tensile reinforcement. Now, how would that be based? How would that design be based on? It will be based on the moments that are generated within the footing. So, whatever the moments that are generated within the footing, we provide a mesh of the longitudinal reinforcement along the length of the footing and distribution reinforcement along the width of the footing. So we are naturally doing this process that reinforcement design has to be longitudinal along the length, and along the width it has to be distribution reinforcement that we are providing. Uh, so thereby uh, the design now uh, of the column isolated footing is complete. But we can also go for further checks, like we can go for a check of the bearing capacity of the footing. We could also go for a check for the what is the if we can go for tapered footing like this. Just let me show you like this. This is a footing design like this, which is tapered footing. And now, why do we require this? Because just now I showed you that there is little tensile forces and little shear transfer of the little movements generated at the top of this. So this is not contributing much to the overall transfer of the load. So thereby, we can have a tapered footing so as to achieve the economy of the isolated footing. So we can go for an alternative design of a tapered footing as well, and that saves our economical cost. So now we'll be taking up the design example for design of the isolated footings.